while we wait for everybody else to show up. Some practice problems to work on. Going through an SN2 reaction. Draw what the products would be. Actually, to make things more interesting, on the last one, change that Br to an OH, and I'll put the relevant numbers in the table here. Good morning. Correct.
Oh, wow.
So those of you who are in this class, you're probably going to be taking enough science classes and chemistry in the future that it's probably worthwhile to know the keyboard shortcuts for subscript and superscript. So control equals will give you a subscript, and control shift equals or control plus will give you a superscript, so that you can, it's much faster than going up to the top and picking subscript and superscript every time you need to write a chemical formula or a charge.
Cool. It's like it with control plus.
It's the same key, just with a shift from in there.
Oh, shit.
So it's the key right next to the backspace. Control equals gives you the subscript. Control shift equals gives you the superscript.
Cool.
H2O, I think it's about 16. Yeah, about 16. All right, let's spend some time on this slide. So the first ones are fairly straightforward. If we want to know the final product, usually that means including any relevant proton transfer steps at the end to make sure that your final product is neutral. It's not super necessary if we're dealing with an amine because at physiological pH, close to neutral pH, most amines are charged. Most amines are protonated. Because you can see that NH4 ammonium has a pKa of about 9. Most amines, especially primary amines, you're gonna have to get above a pH of 10 to get them deprotonated. So in the case of we would never want to leave an alcohol protonated for our final product because that's going to have to get up to a pH of around 15 to 18 for that to be present. But we can be present in large amounts, I should say. But we can leave amines charged, and especially the way this question is phrased, it just says of each substitution following SN2 mechanism. We're really talking about the single one-step, boom, done. So it's okay to leave these charged in this case. And again, you don't have to draw the mechanism, but for the purposes of showing our work here, it can be helpful. Remember, our curved arrows are always electrons moving. So I wouldn't mark you down if you just drew the nitrogen attacking, but it's better to draw the lone pair on the nitrogen because that will remind you not to do this. If this was NH4, if this was ammonium, this can't happen. It can't act as a nucleophile because it doesn't have a lone pair. Right? So it's a good idea when you're doing these to make sure you always show that lone pair. One, because it's better form for drawing your mechanism, and two, just to trigger that. Wait, can I do that? So then in this case, it's SN2, it's concerted. We're going to go through one of those umbrella flips. And it was funny, I actually found a GIF of somebody that had a reversible umbrella. It was titled something like SN2 inversion or something like that. So some chemists had gotten a hold of this GIF where he started with it with the points of the umbrella pointed out and he slid his thing back and it completely did the flip, just like we've been talking about. So in this case, we leave everything else where it is. The bromine's leaving away from us into the board, so the nitrogen's attaching coming out of the board. And it really doesn't matter what the rest of the molecule is, right? And if we're taking care to show all of our reactants, making sure everything's balanced. Right? And then that would then go through a proton transfer where the bromide could act as a base and pull a hydrogen off of the nitrogen to give us that neutral molecule. Again, that's if we're in any sort of polar solvents. I guess in a polar aprotic solvents, they're not that polar really. It'd be tough to say exactly whether we'd be more likely to find it in the charged state or in the neutral state. I would actually have to run some numbers on that to be sure. So again, I'm not going to be picky either way, the way this question is phrased. Which side is favored at equilibrium? Which side is more stable? Starting material or our substituted molecule?
I get confused. It's got to do with the pKa, but I forget how to find that together.
Yeah, so the nice thing is if we're in a polar aprotic solvent, which these all are, we don't need to worry about the solvent effects. The solvent effects are negligible because there's no extra stabilization of our nucleophile. Right? That's when things got weird. So if we're in a polar aprotic solvent, that makes things pretty easy. We just need to go over here and say, okay, well, whatever has the lowest the lowest pKa means it's the best acid, which would mean that the base is most stable on its own. So bromide is all the way down here, the -9 pKa, so bromide is really stable on its own. And remember, we're looking at the conjugate base, not the acidic form. We're looking at the deprotonated form to tie to this. NH3 is a decent base. It's not that stable on its own. So its fact that its pKa is 9 tells us that NH3 is a much stronger nucleophile than bromide. Or to flip that on its head, bromide is a much better leaving group than NH3. NH3 will leave, but not when its competition is bromide. We can replace an NH3 with a hydroxide, because NH3 is a better leaving group than a hydroxide, but it's not nearly as good a leaving group as bromide. So that tells us we would favor the product side at equilibrium in an aprotic solvent. And really, these ones are so far apart in terms of their pKa values. That's a factor of 10 to the 18 difference as far as equilibrium constants go. So even in a protic solvent, this one's going to favor making the product a lot, right? So solvent effects really mostly matter when we're talking about things that are relatively close together. And solvent effect can matter as far as telling us whether we're favoring SN2 or SN1, which we'll get into in a few minutes.
Yeah, the solvent effects are tricky.
They are. All right, if we have fluoride as our base, and we're in a polar aprotic solvent, this is one where the solvent effects would matter, because these halogens are the ones that reverse their strength as a nucleophile. But in a polar aprotic solvent, none of that matters. So fluoride has got a pKa of 3.17, bromide -9. So we would expect fluoride to be a better nucleophile than bromide, and it's going to attack from the opposite side. So if we start with the trans product, we're making the cis. And this side would be favored at equilibrium. The reaction would be the same if we had it in a protic solvent, but equilibrium would be replaced. Because in a polar protic solvent, the fluoride gets stabilized by the solvent way more than the bromide does. So even though the reaction would look the same, equilibrium would favor staying as the reactants if we did this in a polar protic solvent. Right, because bromide is just so much larger physically, it can't be stabilized as much by a solvent the same way that fluoride can. Fluoride's the same size as the atoms of the solvent generally. And so that allows the solvent molecules to get in closer, tighter to it, and surround it more tightly. Really, it's the same logic as to why fluorine is not as strong of an acid as chlorine or bromine. HF is a weak acid. If we go back to our pKa table in general here. There we go. This HI is the strongest of the binary acids, followed by HBr, followed by HCl, and HF is all the way down here. Because HF is smaller, because the fluoride is smaller, it can be bound more tightly to those hydrogens. Despite the fact it's more electronegative, the hydrogen can actually stick to it better because they're closer to the same size. Right, so it's the same logic for the solvent effects. how about down here? We have OH as our leaving group. And we have this happening in water. That's why I had this, why it was a reasonable question to ask. Let's do this in a polar aprotic solvent first. So we're not dealing with solvent effects. I just changed away from being water, so we're not dealing with solvent effects for the sake of this question. You have ammonium and hydroxide. What's our leaving group? The hydroxide. And just like before, our ammonia is coming and attach. That's a lone pair. So our product is going to look a lot like the product from part 1. And then plus hydroxide. Which side of this reaction is favored at equilibrium? Why?
Because the hydroxide is a very nucleophile in the ammonia.
Because the hydroxide is all the way up here. And we're not talking about amide as our nucleophile, NH2 with the negative charge. We're talking about ammonia as a nucleophile. So as it's written here, the reaction would favor the reactant side. If we changed the conditions so that instead of NH3, we were using NH2 with a negative charge, which is called an amide ion. It's a polyatomic ion. It's the conjugate base of ammonia. If ammonium is the conjugate acid of ammonia, amide is the conjugate base of ammonia, the same way that hydroxide and hydronium are conjugate acids and bases of water. If we did this at a pH where we actually were able to have this be in the form of amide, now we're talking about a pKa of 38. So we can replace a hydroxide with a nitrogen. We just have to get to really, really basic conditions. And we can't really go the other way, because the other way we could do this would be to make the hydroxide a better leaving group, right? But to make hydroxide a better leaving group, what do? We protonate it. And if we protonate the hydroxide, or the alcohol group, we have to get down somewhere close to a pH of 0 to protonate alcohols. And so what's going to happen before we do that? We're going to protonate the nitrogen, and now we're going to be dealing with ammonium, which can't act as a nucleophile. So if we want this reaction to favor the products, we can't just make the base of the oxygen a better leaving group in this case. We have to make the nitrogen a better nucleophile instead.
How did that become NH4 when before it was NH3?
Sorry, it's NH3. It's still NH3, it just has 4 bonds.
Okay.
I was counting incorrectly in my head. When I have to think one thing, write another, and say a third all at the same time, sometimes I get jumbled. Would this change at all? Would this particular reaction change if it wasn't in DMSO? If it was in water instead?
It doesn't seem like it.
If we're in basic enough conditions that we can keep the ammonia as ammonia, as long as we don't have the ammonia getting protonated, these are far enough apart in terms of their pKa values that it shouldn't really make too much of a difference. If it's not a hydroxide, if it's a bromide, now we're even further apart as far as our leaving groups. The nitrogen is going to be a lot more stabilized by the water than the bromide will. So solvent effects may come into play. Because remember, all of this is a shifting scale, right? It's not binary, either products or reactants, right? We might be getting closer to it being a 50-50 mixture. But still probably is going, if we're under basic conditions, it's still probably going to favor making the products because NH3 is so much stronger of a base than bromide, even taking solvent effects into consideration. What else is a problem though if we have water as our solvent? Water is a better nucleophile than the nitrogen is. So we wind up, actually no, it's not. No, it's not. It's better on its own. We got all the way to hydroxide. Hydroxide would be a better nucleophile than ammonia. But it is a nucleophile, which means we still have to deal with the fact that water could be getting in there and making other products. Really, we're not going to wind up with just one product if we do this, because you're going to have a mess of water molecules getting in there. It's going to be a statistically, you have two equilibrium reactions happening at the same time, which means you're going to have, they call nested equilibrium reactions or linked coupled equilibrium reactions. And if you have this at a pH where this is deprotonated, that means you also have a significant amount of hydroxide around, and the hydroxide is a better nucleophile than NH3 is. So really, we wouldn't want to do this in water. In fact, there's a reason we hardly ever use water as our solvent in OChem, is because nucleophilic attack is one of our 4 basic mechanism steps, right? We almost never want to add an extra nucleophile. The one time we might do this in water is if we were specifically wanting hydroxide to be our nucleophile. We could use water as, you can use the conjugate acid of your nucleophile as the solvent without throwing things off, right? So it's pretty common to use methoxide and, as your nucleophile in methanol. So methoxide is just a deprotonated form of methanol. So you could do a reaction that looked just like this one. And with CH3O minus as our nucleophile in methanol. Because if this acts as the nucleophile, you're going to get the same product either way, but just the protonated form. Right, so generally speaking, a lot of times you will see things written, you might not even see it written like this. Sometimes you see organic chemists get really, they try to be efficient with their space, if I'm using generous assumptions here. And they'll write things like NaCH3O / CH3OH, instead of even bothering to write out plus the methoxide. They'll just write it like that. And you're supposed to be able to look at this and say, oh, well, that's a nucleophile. Therefore, and this is the solvent. And you see them paired up a lot like that. You can do the same thing with ethoxide and ethanol. All right. So let that marinate for a second, and answer a couple quiz questions. Somebody asked if there have been studies on mixing the different types of vaccines. There have not been studies specifically, mainly because it takes so long to run a statistically significant study. You've got to get a control group, you've got to get tens of thousands of people in each category that you're studying. So that would be tens of thousands of people that got a booster where it's Pfizer, and tens of thousands of people that were Moderna, and tens of thousands of people that were mixed, specifically Moderna first and then Pfizer, and then tens of thousands of people where that's reversed. And then you have to watch them over a long period of time to determine whether or not they have boosted immunity, which means basically you look at them and see if they had a higher a higher incidence of COVID infection compared to the average population that was unvaccinated. To see, and then you compare all those numbers to each other. So basically, there just hasn't been enough time and data. We're not tracking this enough because we just want to get shots in arms. And so it's not as much on people's radar. And so they do know that it's still, regardless of what your first vaccine was, the booster is still helpful because all these different vaccines are doing is they're introducing either the traditional vaccine like the Johnson & Johnson one, they're just introducing like bits of viral protein into your body to let your immune system learn to recognize it as being foreign. And once your body recognizes it as being foreign, it remembers that and will attack any live virus that comes in. The mRNA vaccines do the same thing, except that they have your own cells make the viral protein, bits of it, a denatured form of it. And so it doesn't really matter which version you're getting, you're still getting sort of this shotgun scattershot approach of we're going to make a bunch of denatured viral proteins and let your body learn to recognize it. And so it doesn't really matter which viral proteins necessarily. And that's why for some people they get lucky and they get 100% immunity because their immune system happened to latch on to the few bits of viral protein that are always present in COVID. And other people, their immune system learns to recognize things that mutate really quickly. And therefore their immunity doesn't last as long. And so really, herd immunity really becomes a big deal with these because you're relying on the fact that, okay, well, my personal immunity may be gone. So I'm relying on the fact that everybody else still has their immunity to limit my exposure to COVID. This applies to anything, right? We don't need to vaccinate for smallpox at all anymore because there's zero chance of running into it in the wild. But for things like measles or rubella, we still do need to vaccinate because there's still a chance. We need to keep the herd immunity for right now so that if there is an infection, the odds of it hitting somebody who doesn't have an immunity from a vaccine is next to nothing. If 19 out of 20 people are vaccinated for measles and that one person gets the measles, the odds that they run into somebody else are almost none. That every person they run into is a 5% chance. But that's low enough odds that it won't cause an outbreak because what they call the R value, which is the average number of infections that you can cause before your immune system knocks down an infection, is low enough that you're likely only going to come into contact with 3 people, say, anyway, where you could actually spread it. And so if the odds each of those 3 people is 1 out of 20 is 5% chance, that's only a total of 15% chance that you could actually spread it. And then if each of them has a 15% chance of being able to spread it, it knocks down the spread in the entire community. And so that's why and I'm ranting a bit here, but that's why the argument well, my immune system is fine, I don't need to deal with that, or I don't want to deal with that, or it's just a really selfish argument because it's more about civic duty and protecting the people around you and slowing the spread overall than it is about you personally. Yes, it helps you personally too, But even if you're willing to take that risk, other people might not be willing to let you take that risk for them. Yeah, immunology is really, epidemiology is basically, so immunology is what Carl does, right? It's a study of viruses, infection, and the immune system's response. Epidemiology is basically applied statistics to the spread of diseases. And that's an incredibly fascinating field too, especially if you like statistics. Is there a situation in which manipulating stereochemistry through repeated iteration of substitution reactions is energetically or economically favorable? Seems like an awful lot of work to try to get one specific stereoisomer. And it is sometimes. The problem is that the potential downsides to not doing that, especially if you're dealing with a pharmaceutical, are really, really high. Like thalidomide is the one that always gets used as an example. Have we talked about that in this class yet? So, Gen Chem maybe? So now that you know more about OChem, let's pull up the structure. It's a classic case study because it also illustrates how well the FDA falls down sometimes, but it's a classic example of why we have these regulatory agencies. So R and S thalidomide, one of them is a very effective anti-nausea drug, and the other one stunts cell growth and has no effect on nausea. They didn't know the stunt cell growth thing in the 60s, and so they started prescribing thalidomide as an anti-nausea drug for women who were pregnant for morning sickness. But it was a lot of work to try and make just one of them, and it cut their yield in half to purify it. So, and it adds another step in the process. So they were actually prescribing it as the racemic mixture of R and S. And so, in addition to being really effective at knocking down the nausea, it also stunted the cell growth of the fetus. And so, this was really only happened for about 9 months in the 60s in Europe, and basically babies started being born, missing limbs, sort of horrific birth defects that was the direct result of the fact that they were being given a racemic mixture instead of just the anti-nausea one. And in the U.S. that didn't happen though, because there was a woman whose name I'm forgetting right now, who's basically like stonewalled getting this drug approved because she said that it hadn't been tested enough. And as a result, we didn't have any of these birth defects in the US because the FDA did its job and it actually stuck to, in spite of being pressured from the pharmaceutical industry to approve this, they did not approve it for long enough that then they were able to see these effects, and it worked out okay for America. Of course, that was before the industry capture. In fact, the FDA is now run by a lot of people that actually have financial interests in pharmaceutical companies. They still do an okay job at what they do. It's a little bit less trustworthy now. Regulatory agencies are supposed to have sort of an adversarial role towards industry as opposed to being part of industry. But you saw the same thing with the EPA, and I think I can make this generalization without being wrong. If you look at anybody that was appointed by Donald Trump, it was an industry capture appointment. Anybody that was appointed to any of the regulatory agencies was a member, a lobbyist for that industry. And basically weakened pretty much all of the regulatory protections that we have. So that's a problem when you make the head of the EPA somebody who's worked for oil companies for the last 30 years. Anyway, so not to weaken so that's sort of the flip side of the coin to talking about the vaccine and the vaccine is under so much scrutiny, the data is publicly available, that the vaccine, COVID vaccine can be trusted, but a lot of these other drugs, really it's the opioid epidemic is a very good illustration of what industry capture in pharmaceuticals can do to the population. So are there cases where it's favorable? Absolutely. Sometimes when it's necessary. Interestingly, there is a silver lining to the whole thalidomide thing. Thalidomide, the one that stunts cell growth, is actually being investigated as a cancer treatment now. Because if you have somebody that you know isn't pregnant and they have this malign tumor growing and you want to slow that down, thalidomide's actually a really good candidate for that. And the other one is still a really good anti-nausea drug. It just doesn't get used anymore because it got, it has such a negative public perception after that, understandably. And the average consumer doesn't understand the difference between an R and an S and anti-R. So basically, it's totally gone as an anti-nausea drug, because there's other things we use instead.
Just to kind of clarify what I was really asking about is whether the mechanism of doing like repeated like SN2 substitution reactions and then reiterating it in a way where you get maybe an elimination or SN1, is that like a reasonable way to manipulate stereochemistry? Or is there other ways that are better?
So the problem with doing repeated SN2s is you can only go back and forth, right? And so you have to end, if you want to flip the stereochemistry, you have to end on an odd number. Or if you want the same stereochemistry, you have to end on an even number of reactions. There are cases where we can wind up with elimination reactions that give us a very specific stereoisomer that then we can go through one step there. So it's not always just through SN2. There are other options in there that are, depending on the case and what we're starting from and where we're trying to go, might be better. We just haven't gotten there yet.
I feel like a lot of it's just purification too.
A lot of it is purification.
Pull out the R, do it again, get more R.
Yeah, so if you wind up making a racemic mixture, we can still purify it, which is weird. You can tell that you made the mixture because the melting points will be off. The R and the S, when they're pure, might have the same melting point, but when they're mixed together, the melting point drops because it's impure. They basically throw off each other's crystal structure. If you have a bunch of right-handed screws that can pack together so tightly that their threads are are in between other threads, if you throw a left-handed screw in there, it can't fit in there the same way, right? Its threads are going the opposite way, so they can't nest in together as well. So with that in mind, you can actually you can see that the melting point drops, and then you can separate them basically by using a similar technique. If you do column chromatography, but you attach something to the surface of the beads where it's, whatever you attach the beads is only the R stereoisomer, then the R stereoisomer will go through the column slower because it can basically nest into those R isomers that are on the surface of the beads better. So we actually have ways we can separate out R and S from each other pretty reliably and with pretty high yields, which means that it's not necessarily the end of the world if you make the racemic mixture. You just have to then purify it, and you're cutting your yield in half unless you have a way to take the enantiomer you don't want and turn it back into something useful. So for instance, it's a good example, we use methamphetamine. One stereoisomer of methamphetamine is actually, you can actually buy it at Raley's. It's used as a decongestant. Those little mini inhalers you can get have one of the stereoisomers of methamphetamine in them. It's not the one that gets you high. The one that gets you high, though, still gets prescribed in extreme cases of narcolepsy or ADHD. So the pharmaceutical industry, they can make it both versions of it and then separate them out, market one as a decongestant and the other one as a prescription for ADHD, and they're making money on both sides. It's not really a waste in that case.
There's some cases though, like the thalidomide, where you really have no use for one of them. You only want to make the opposite, and that's where you want to really focus on the stereochemistry.
Or the flip side, if you're Walter White, you really only care about one of the stereoisomers too, right? You don't want to mess up your stereochemistry because then you're cutting your yield in half. All right, so this is a table that's looking at, this is the wrong keyboard. That's looking at solvent effects on rates. So if we have, and this is just looking at the halides. Most of the time with solvent effects, we're going to be most interested in the halogens because those are the ones where we can really predictably rank them by their nucleophile strength in either protic solvents or aprotic solvents. Right? When we start getting into hydroxide versus amide ions, I don't necessarily expect you, I expect you to understand that the solvent is going to affect it, but it's kind of a little bit unpredictable at this point. But for these halides, if we look at the relative rate in methanol, which is a protic solvent, with bromide as our nucleophile, we're going to use that as our standard. Chloride is about 25 times slower. And fluoride is about 25 times slower than that. And the flip side, the iodine is 40 times faster as a nucleophile, which is opposite of what we would expect from their pKa's, right? So in a protic solvent, it reverses their nucleophilicity for these halides. If we do it in DMF, we see the exact opposite. One, bromide itself goes 20,000 times faster. And then relative to the bromide, that's a factor of, now the iodide is, what is that going to be, about 3 times slower? And it was 40 times faster. Right, so everything gets flipped. One, all of the reactions happen much, much faster if we're going SN2 in an aprotic solvent. And the rates relative to the other halogens flip. In an aprotic solvent, everything behaves just the way we would expect from their pKa. So that's sort of the simple case. When it's a protic solvent, things get weird. And their nucleophilicity reverse. And so fluoride in an aprotic solvent is up 50,000 times faster than bromide in a protic solvent. And that's comparing apples to oranges a little bit because we changed both the nucleophile and the solvent. But just to give you an idea of how drastically these rates can change, because it's always going to come back to, rates are always going to come back to this version. And really what we're doing when we mess with the solvents is we're changing the activation energy because we're stabilizing the reactants, we're stabilizing the nucleophile, which is going to increase your activation energy. So I mentioned that I did computational chemistry where we're calculating transition state energies. And the rule of thumb that in our lab, for just to have a way to compare these numbers, to give yourself some numbers, is that a jump of 5 kilojoules per mole in the activation energy was a factor of 10 slower at room temperature. And if you went another 5 kilojoules per mole, it was 100 times slower. It's that exponential relationship because it's in the exponent here. Right, so pretty small changes in the stability, and that's 5 kilojoules per mole. That's, if you might not remember, but if you think back to some of the different conformers we were talking about, like going from chair to a boat conformer can be a difference of 10 kilojoules per mole. Right, and that's just a conformer change. That's not even an actual bond breaking. So changing an activation energy by 5 kilojoules per mole is almost nothing.
It's really easy to do, which is why we see such drastic changes in the rates here. Switching solvents for fluorine means it goes 82 million times faster at the same temperature and at the same concentrations. All right, so this is sort of a complicated graph, but it's a good summary. The strongest base will also be the strongest nucleophile unless both of these are true. Right, so here's our bullet point here. If the reaction occurs in a protic solvent and the bases differ in size. If we're talking about everything that's still on the same row of the periodic table, that's close to the same size. And so if everything is in the same row of the periodic table, we don't need to worry about this. We can still just look at it as strongest base is the strongest nucleophile. If the reaction occurs in the protic solvent and the base is different size, and again, the bromide or the halides are going to be our most obvious example of this, because we don't do a whole lot with like sulfur as a nucleophile yet. If we were looking at sulfur versus oxygen as a nucleophile, we could make similar connections. But sulfur is not used nearly as much. It's not as nice to work with as a lot of these halogens. And I believe that this table is in the textbook in the end of the chapter material on substitution reactions. There's a couple good, really good handy graphics that have a lot of these generalizations. So increasing size means it's a worse base, therefore a worse nucleophile, unless we're talking about a protic solvent. So better nucleophile, worse nucleophile. All right. So let's review at these substitution. This is our bullet points recaps of reactivities. SN1 versus SN2, again, same steps, just one of them is concerted and one's happening in stepwise. Which one is stepwise? SN1. SN1 is first order, right? So it means leaving group leaves first. If a reactant in the rate determining step is charged, more polar solvents lead to a slower reaction, or specifically protic solvents, because we're stabilizing the nucleophile. If the reactants are neutral, then more polar solvents generally lead to a faster reaction, because increasing the polarity of the solvent doesn't really overstabilize the nucleophile. And really, polar versus protic is really going to make, or protic versus aprotic is really going to make a difference in determining which of these pathways we go through. So we're talking about things where it's 82 million times slower if we're in a protic solvent, but protic solvent is also stabilizing an intermediate for SN1. We can basically, it's almost like flipping a light switch. We can switch back and forth between SN1 and SN2 by changing the solvent. Because we can effectively, in terms of sig figs and measurable amounts of product, we can effectively say SN2 does not happen compared to how quickly SN1 is going to happen if we're doing it in water, say. Right, so, and here's a slide where we talk about that. So for SN1 reactions, let's look at this one first. If the red is the more polar solvents, and protic is the most polar solvents we're going to have. If the reactants are more charged, then more polar solvents mean we're going to stabilize the reactants more in a more polar solvent, which is going to slow things down. In a less polar solvent, we're sitting up here, our reactants are less stabilized, so it's easier to get to the transition state. However, the other possibility is if our reactants are charged, if our transition state is charged or our intermediate is charged, we're stabilizing a different part of the potential energy surface. Right, so by switching to a more polar solvent, if we're making a carbocation intermediate, we're stabilizing that a lot with a protic solvent. Because it's got a full charge, right? The more polar our solvent, the better when it comes to stabilizing an intermediate. So we're going to favor SN1 reactions when we're going to a more polar solvent compared to SN2, where it still has to be polar enough that we can get our nucleophile to dissolve, but we don't want to stabilize our nucleophile too much. Right, so summary of substitution. I know I already said that once, but I mean it this time. SN2 reactions are favored by strong negatively charged nucleophiles in an aprotic solvent, strong neutral nucleophiles in a protic solvent. If you have to use a protic solvent, your nucleophile better be neutral if you want it to go SN2. If it's neutral, it's not going to be surrounded by the solvent as much. Less substituted active carbons. So primary, a leaving group being on the primary carbon is better than it being on the secondary carbon, etc. So less substituted is better for SN2. And bad leaving groups. A poor leaving group will favor SN2 because for SN1, the first step is leaving group leaves, right? If you have to wait for your leaving group to leave before the rest of the reaction can happen, if you have a bad leaving group, that's not going to be as likely. If you flip these all, you get SN1. If you have weak nucleophiles in a protic solvent, then you're going to favor SN1 because you're going to stabilize the intermediate more than your nucleophiles. More substituted active carbons because a tertiary carbocation is more stable than a secondary and so on. Resonance didn't show up here. Resonance doesn't really affect SN2. But if you can have any resonance happening that can stabilize your intermediate, that's going to make SN1 more likely as well, right? So being in an allylic position or being in the benzylic position adjacent to a pi bond, not attached to the carbon in a pi bond, but one carbon away, is going to favor SN1 reactions, and it makes no difference for SN2. It's not to say that resonance, if there's resonance, that means SN2 is less likely, it just doesn't play a role really. And good leaving groups, you have to have a good leaving group if it's going to go SN1. All right, let's take our break. Let's come back at 5 after. And we'll predict which mechanism and the products for these reactions.
Without the sodium cyanide, do you consider it a charged nucleophile or not charged?
So the sodium is not going to be acting as as the nucleophile, right?
Yeah, they'll disassociate when they're in your solvents, right?
Right. So it's really just the cyanide that is the nucleophile. So what does that tell you?
It's gonna be charged.
Yeah.
So something like ammonia would be an example of a non-charged.
Or water, or ethanol or methanol.
Okay.
Anything with a lone pair, right? Anything with a lone pair could be a nucleophile.
Yeah.
It's just a matter of, is it charged, is it an ionic compound, or is it neutral on its own?
Yeah, I was getting hung up thinking most nucleophiles are going to have a charge on them, but there's plenty of examples of most of them.
Yeah, and a lot of times the most common nucleophiles will have a charge, because if they're stronger nucleophiles, then that means the reaction usually goes faster. And usually we want to favor the more specific mechanism, right? So generally speaking, SN2 is preferable to SN1. Because SN1 also opens the door to rearrangements. You have other things that can get in there and react, because you're making a really reactive intermediate. So SN2 is usually favored unless there's some reason why you can't use it, or you want the mixture of products. You know, occasionally, if there's no other way to get the product you want, sometimes you have to do a reaction with a really low yield and then purify it. So yeah, so maybe you only get 15% yield on this step of the reaction, but it's the only way to start from a cheap precursor and make something that is really valuable for some reason. 15% is okay if there's no way to make it better.
Yeah, especially if you do it on a real small scale, right? If you're just
Small scale, or even there's a lot of stuff where precursors, natural precursors tend to be really, really cheap.
Right, right.
Like, so eugenol from clove oil, cloves are cheap, relatively speaking, compared to having to buy a precursor from a chemical supply company that they had to make by hand. So sometimes it can be better. You could get, maybe if you bought this, we have precursor A that is, I don't know, $15 per mole, and you can get 10% yield to get the product. Versus precursor B, you could get 98% yield, but it costs $150 per mole. Well, if we want to know which of those is better economically, you have to run the numbers and say, okay, say I spend $200, how much product could I make? And compare those two things. And then, if these are maybe not even that, a lot of times it's even bigger difference. There's a lot of times where your precursor, if you're using a natural product, is actually waste in some other industry. Or could get even cheaper. And so,
I heard that's where some of the original caffeine came from, was discarded tea leaves from the tea trade that were damaged or whatever, and some chemical company out of Germany, I think, was extracting the caffeine and selling it to companies like Coca-Cola and stuff.
yeah, a lot of times if you want, extractions are really useful that way, because something doesn't look good enough, it's like imperfect foods.
Yeah.
Right? Something that's not good enough, doesn't look good enough visually to sell, can be repurposed. Actually, that's the same thing they do with canned fruit. I had one of my buddies in grad school, his mom worked, I don't know what the company was, but basically worked on one of the companies where they took all of the carrots that were too ugly to be sold as carrots, and that's what they did, and then turned them into baby carrots. You basically just sand off the rough edges. That's where baby carrots come from, is the carrots that can't sell as real carrots. And same thing with peaches, and canned peaches, and bananas, and all sorts of stuff. You get baby food from bananas that can't sell because they're ugly. Right, so engineers are very clever that way. Oh, you've got waste? And actually, a lot of companies, like, we have all this waste, who could we who can we get to buy this from us instead of us throwing it away? So a lot of times, and when you're dealing with these scales, you don't just get to throw away your waste. You have to pay people to take away your waste, because otherwise it accumulates and causes problems in sewage systems. So even just breaking even on your waste can actually make the company money. One of the more interesting classes that I took in grad school was a class called bioprocess engineering, which, not coming from an engineering background, I didn't know what that meant. I thought it was like metabolic pathways, and we were going to be doing like, learning techniques for genetic engineering. But process engineering is actually the study of how you build a factory to be efficient. So bioprocess engineering was, here we're going to use this genetically modified yeast cell to produce a specific amino acid. And so you have to design a factory. Our final project was a group project where we had to design a factory that had a bioreactor where all the yeast cells grew, and we had to put it through a bunch of purification steps, and we had to plumb in heating because you have to keep the reactor at a certain temperature. We had to deal with the electrical and where's the waste going, and how do you physically move it from this bioreactor to that bioreactor, and then what do? We just centrifuge it. Like what RPMs do we centrifuge it so that we separate the yeast cells out, but not the amino acids that we want to keep? So it's a really, really cool field.
Yeah, I heard the startup company that is using genetically modified yeast cells to produce THC and similar compounds.
It's not a new field either. It's new being used for those particular drugs, but that's actually where all the human insulin comes from. So they use genetically modified yeast. They insert the gene for insulin into yeast, which yeast has no reason to have a gene to produce insulin because yeast is a single cell organism, right? Insulin is designed to communicate between different tissues in a larger organism. So basically you insert the gene with a bunch of promoters in front of it into yeast's genome, and it just cranks out insulin. And then you just lyse the cells, purify it, make sure you don't denature the insulin along the way, and now you've got human insulin produced from a lab.
Pretty amazing how nature makes chemistry super easy.
It does sometimes. Before they knew how to do that, they actually used pig insulin. They actually sold the glands of pigs when they were butchered, got sold to pharmaceutical companies, and the pharmaceutical companies had to process the glands, livers, and thalamus, and all the glands that produce insulin. And pig insulin is close enough to human insulin that it could keep diabetics alive. Although what didn't work nearly as well as human insulin, caused a lot of allergic reactions. If you happen to be diabetic and allergic to pig insulin, then you're just dead. You're out of luck.
Sounds fun. Just go to the butcher shop, there's a blender.
Right. Yeah. So it's a lot cleaner and more sanitary these days to use genetically modified. But yeah, THC is an interesting one because you have to take, so clearly one plant in particular has the gene for producing THC and CBD and all those other relevant molecules. So if you can take that gene and get it to insert into yeast, yeast is a good model organism because it's a fungus, but it accepts outside genes pretty well, and it's pretty well understood metabolism. Plant genes going into yeast is not something I've heard too much about, but it makes sense, especially if you can isolate, now that it's less stigmatized and more legal, there's more research going on. Before, it would have been hard to even get scientists to admit they knew which gene was responsible for THC production up to about 10 years ago. But that's all changing, and that in general, should lead to better yields at the very least. And really what you're seeing is that startup is going to be very quickly bought up by one of the big pharmaceutical companies that already have the bioreactors and all the process engineers to do the designing. They file a provisional patent or on the idea of using GMO yeast to make THC, and then that patent is what the actual companies are then going to buy. And then most startups, that's the end goal for most startups, is to get bought by one of the big companies. And you get your payday and you move on to another startup, or you retire when you're 25. Right. Right. Who's it that's, there's somebody in particular that's famous for doing, he made his money, made $1 billion, and then just disappeared from the public scene for like 25 years. He just like literally bought an island and lived on an island for 25 years. I can't think of who it was. Probably somebody from the tech bubble in the 90s. All right, let's look at these. Again, if we're trying to decide SN1 or SN2, that's the first step to figuring out what our product is going to be, right? So if we want to know SN1 versus SN2, strong nucleophiles favor SN2, good leaving groups favor both, really. But so stronger the nucleophile, it's going to favor SN2 more, and the aprotic solvents favor SN2 more. Those are the main things to look for. And then number of carbons on our active, attached to our active carbon. So like free vectors. And probably in order of importance, it's number of carbons attached. I'll put 2 and 2. They're roughly the same. They're tied together. Nucleophile strength and solvent are going to be related to each other. So I'm putting them both on the second tier. All right, so if it's a secondary carbon, that means we can't rely just on one, because secondary carbons can go through SN1 or SN2. So now we're down to looking at, okay, how strong is my nucleophile and what's my solvent? So in this case, cyanide is a pretty good nucleophile. It still could go SN1 or SN2, except for the fact that solvent is sort of our deciding factor in this case. So if it's a strong nucleophile, that still does not 100% tell us what we're doing. If it's a weak nucleophile, that can be enough on its own to tell us it's SN1. But if it's a strong nucleophile, we then need to consider solvent. Right, so good leaving group, strong nucleophile in an aprotic solvent on a secondary carbon, SN2. Which means our product is going to look like that. So cyanide, we haven't used that much as a nucleophile. So it can be helpful to go back and maybe review what the Lewis dot structure might look like for some of these less common nucleophiles. Cyanide is CN with a negative charge. Lewis dot structure looks like this, which means the carbon has a negative charge in the lone pair. So this is a case where carbon can act as a nucleophile. It makes it kind of useful, right? Because we haven't seen very many of those yet. There is also a lone pair on the nitrogen, so you actually can wind up with the wrong end of a cyanide attaching to something, and then you wind up, we call that an isocyanide, because it's less common, because more of the carbon is more reactive as a nucleophile than the nitrogen is. But you can wind up, you're going to wind up with some small amount of the nitrogen attached where I've drawn the carbon attached. Still a secondary leaving group. Leaving group's on secondary carbon. So again, that's not going to be enough to determine SN1, SN2. Still a good leaving group. Much weaker nucleophile. Water's neutral, right? And if waters are nucleophile and it's the solvent, we're also in a protic solvent. Protic solvent, weak nucleophile favors SN1, yeah. Which means you might want to stop to draw the intermediate and make sure there's no rearrangements that could happen. So our intermediate here would look like this. Any rearrangements to worry about? I haven't explicitly said it, but we're only looking at rearrangements where you can make it, turn it into a tertiary. If you can turn a secondary carbocation into a tertiary with only one step. We don't do multiple rearrangements in a row. There's not enough thermodynamic force to drive that. So that means if we move the hydrogen from over here, it'd still be secondary. If we moved it from over here, it'd still be secondary. So no rearrangement. So our product, and I can draw a better pentagon while I'm at it. I'm not sure if it's any better. It's just wrong in the opposite direction. Final product would look something like this, and you get the R and the S. So either show both or write R plus S to show me that you know that that's still a stereocenter. You just get the racemic mixture. Side note about polygons. Be amazed what they're teaching kids in kindergarten these days. At least I was. Be amazed what they're teaching kids in kindergarten these days. At least I was. Son came home from kindergarten after like 3 months of kindergarten and he was counting the vertices on a cube. Mentally.
What?
Like they have them counting, and in Spanish too, which meant it took me a while to figure out what he was actually talking about. But yeah, like, you know, hexágono tiene 6 vertices. Yeah, I was very surprised by that. A lot of stuff that we did in first grade, they're not doing in kindergarten now, which is kind of cool. All right, last case here. Not quite as good of a leaving group. So push comes to shove, that might favor, chloride's still a good leaving group, just not quite as good as bromine. So push comes to shove, that might push us in the SN2 direction. That's sort of a last ditch. We really can't make a decision. Everything else sort of balancing out. And it's also, in this case, if I wrote this on a test, it'd be okay to say, you know, here's my logic. I think both mechanisms are gonna happen about the same amount. So I'm gonna write the products from both from both mechanisms is a valid answer if you can't make a determination. You might be wrong, but if you can explain your logic and your logic is consistent, then I can still give a lot of the partial credit for that. All right, so mediocre leaving group, mediocre nucleophile. So weak nucleophiles favored SN1. Bad leaving group favors SN2. Aprotic solvent favors SN2. So this is one we're kind of right on the border. Aprotic solvent means we can just look at the nucleophiles in terms of their pKa values, right? Chloride's a -7. Methanol is all the way down here as we're looking at this one. As our nucleophile, methanol's our nucleophile, we're looking -2 versus -7. Right.
DMSO.
Dimethyl sulfoxide. So basically there's a list of common aprotic solvents. It's DMSO, acetone, DMF, which is dimethyl formamide, there's just a couple really common ones that you just want to recognize as, hey, that's one of my aprotic solvents. And anything that has a hydrogen attached to an oxygen or a nitrogen is going to be a protic solvent. So any alcohols, water, any amines as a solvent are protic solvents. All right, so probably this being in an aprotic solvent, in an OK nucleophile, we'll probably expect this to go SN2. The solvent is really our deciding factor in this case. Our nucleophile is strong enough as a nucleophile. And our leaving group's not a great leaving group, but it's good enough that we can use this. If we did this same reaction in methanol, we would expect SN1. But the fact that the solvent is VMF means we're not stabilizing that intermediate enough to say that it's going to go SN1 predominantly. It'll be mostly, basically you have to have a protic solvent to go SN1, and because you have to be able to stabilize that intermediate enough to make it viable.
But if it's different product, if you're putting it in the protic solvent, okay?
Well, it depends on what your protic solvent is. If your protic solvent is methanol, then no.
I was thinking.
Oh, because of rearrangement. Yeah, you're right. So if it's SN2, we get so first step would be this, and then we would need to deprotonate. If we did this in methanol as our solvent, and a lot of times we wouldn't even write plus methanol in that case. We would just write this in methanol. Now all of a sudden we wind up with it going SN1. If it goes SN1, our intermediate, we lose all of our stereochemistry, right? And our intermediate looks like this, which can go through a rearrangement. The hydrogen that's over here can move on over, and we wind up making an intermediate that looks, a second intermediate that looks like this. And now this is where the methanol would come in and catch. So not only do we lose our stereochemistry, we actually made a compound that doesn't have any stereochemistry, right? So if it didn't rearrange, we would still wind up with a mixture of RNS. But it rearranging means that we have a methyl group, an ethyl group, and an ethyl group. In fact, if two ethyls are identical means that this no longer has RNS. Okay. All right. So we spend a lot of time on substitution because, one, this is our first good look at how mechanisms work in general and all the different variables that can go into a method. Right, knowing that you can't just look at the reactants and draw the products because you need to think about, well, which of the two possibilities does it go through? That's tricky, and we're going to continue that, but it's going to be the same variables in a lot of ways when we add our next. Here's some more practice that we'll do. Might save some of that for the quiz. There's another set of mechanisms that will compete with the same reactants. So if you have a good nucleophile and you have a good leaving group, it can go substitution, but the other possibility is you can actually have to go through what's called an elimination reaction, where instead of just replacing a good leaving group with a nucleophile, if the nucleophile acts as a base instead, it can actually pull a hydrogen off when your leaving group leaves, and you wind up making an alkene. Right, so elimination reactions, they're called elimination reactions because you're removing things from the molecule. And so, for an example, using one of the ones we just went through to show you what the net result looks like. If this molecule went through an elimination reaction, it would be this bromine leaves, and then instead of being replaced, you pull off a hydrogen from one of the adjacent carbons. And that hydrogen, and then when you pull off that hydrogen, the extra pair of electrons that was right there. So it actually, in terms of a mechanism, it almost looks like it's similar to a rearrangement step. If we have something like hydroxide that can act as a base, it can come in here and steal a proton. Instead of attaching right there, it could steal a proton instead. And when it steals a proton, those electrons have to go somewhere. So the electrons move over to make a pi bond. So your product looks like wherever your leaving group was, loses the leaving group, and then one of the adjacent carbons loses the hydrogen to make an alkene. And we'll talk about which version is more stable here, but basically you have two adjacent carbons, right? You have two adjacent carbons, there's two places you can steal a hydrogen, which means there are two possibilities for where to put your pi bond. Okay, but the basic idea of an elimination reaction is just that. Instead of your nucleophile attaching, it steals a proton and acts as a base instead. Because most of our things that are good nucleophiles are also good bases, right? They're good nucleophiles because they have a negative charge and they're not stable on their own. They want to make another bond. They can do that by attaching to a carbon or by stealing a proton. Brad?
So theoretically speaking, for that reaction to take place, would we be putting it in water initially, most likely? Or would it be anything with the OH group?
So you can use hydroxide as a nucleophile in an aprotic solvent. We'll talk about solvent effects, whether it goes substitution or elimination as well. So we would want to choose how to do this in a way that promotes, if we want the elimination to happen, we want to minimize the substitution. So we would want to look at the solvent with respect to that too. So we'll get there. All right, so elimination reactions pretty much only happen when you've got alkyl halides with strong nucleophiles. Why might that be the case? And if your first instinct is to repeat something I said a few minutes ago, then you might be onto something. What's true about strong nucleophiles? They're also
Good bases?
good bases.
So they're like full hydrogens.
So they'll pull anything. They'll pull. And predominantly with alkyl halides because you also need a good leaving group. If you don't have a good leaving group, it's really hard for an elimination reaction to happen because you need your base to be attracted to a hydrogen, and simultaneously, or first, you need your leaving group to leave. All right, and so just like with substitution reactions, we have two different mechanisms. SN1, SN2 was first order, second order, right? Concerted for SN2, stepwise for SN1. Elimination reactions, you have E1 and E2. Makes sense, right? What do you think 2 and E2 stands for?
Concerted versus stepwise?
It's concerted versus stepwise, so the E2 would be which?
Concerted.
Concerted. E1 is stepwise. How could an elimination reaction be first or second order? What would first order look like? What's first order substitution look like? Yeah, because what's the first thing that happens? Leaving group leaves. So E1, we would expect the same first step, right? If it's first order elimination reaction, the same first step is leaving group leaves. That's the one that I drew up here as the intermediate to show what was going to happen. How could it be second order? Let's see.
I was gonna say, it just happens kind of simultaneously, that seems kind of grossly oversimplified.
So let's say we've got bromoethane. We could have leaving group leave, and then a base steals a hydrogen to make ethene. Or we could have our leaving group leave at the same time as the electrons are moving over. So we could have all of that happening simultaneously. Okay?
When we say simultaneously, how simultaneous are we passing, like instant?
Instant, because we're talking about orbitals, right?
Yeah.
We're talking about as things are moving, the orbitals are shifting. So if it's simultaneous, we mean that this bond is breaking at the exact same time as these electrons are, the orbital for these electrons is shifting into being a pi bond. At the exact same time that this orbital starts to look like the anti-bonding orbital, and this orbital, this bonding orbital starts to form all at the same time. So you can actually wind up with cases where you find some really weird looking orbitals at the transition state, because it'll actually look like this sigma bond is also half of a pi bond. And that half of a pi bond is going to a carbon that has got an anti-bond orbital starting to form. Right, so it's, when we say instantaneous, we mean simultaneous, the exact instant. All of this is happening in real time because these electrons are moving so quickly and are existing as these clouds anyway, these wave functions anyway.
Do you think it would be possible that it would be going faster than the speed of light, or no?
No. I think we can say that, and we're dealing with distances that are so small, it'd be really, really hard to tell if it was.
Yeah.
But considering we know that gravity acts at the speed of light, and every other form of energy transfer operates at the speed of light, we would think that these are also operating at the speed of light. Good question, though. All right, let's talk about naming alkenes. Since we're making alkenes, we got to be able to name them. So a little bit of a break from mechanisms to think about something that you're maybe feeling a little bit better about. Nomenclature. Alkene nomenclature, and we've already touched on this a little bit. It's the same rules as an alkane. Find your longest continuous carbon chain that has the pi bond in it. And then instead of adding ane to the end, you get ene, E-N-E. I resized all of my font last year for presenting on Zoom. And sometimes that means it's too small now. So instead of ethane, we get ethene. Instead of cyclohexane, we get cyclohexene. Easy enough, right? Except occasionally, when we get to larger molecules, we need to specify where the double bond is. So this butene would be the parent molecule. We just need to say where that double bond is. And so we do that with the locant. Right? Just like with anything else. Except we only specify the first carbon. Because if the pi bond starts on carbon 1, it has to be going to carbon 2. So there's no need to say 1,2-butene. It's 1 butene implies carbon 2 is next to carbon 1. And so we're sort of assuming that everybody counts sequentially, which is, I think that's a valid assumption. And so, I think technically the IUPAC way of naming these now actually puts the locant in the middle of the molecule. because that allows you to add multiple suffixes to the same molecule. But it doesn't look nearly as good. So 1-butene rolls off the tongue a lot easier than butanene. There will be times where we'll stick a locant in the middle of our parent molecule, but usually when there's going to be more than one functional group at the same time. So for instance, if we had this molecule, and actually that's a stereocenter, but that's not the point I'm trying to make. We could name that as cyclohex 1-ene 4-all. The 4 is applying to the OL, which indicates an alcohol. Or you could say it as 1-cyclohexane 4-all. And so there are some times where it's not really, we can't really get away from sticking a number in the middle occasionally, but those are going to be sort of the exceptions. We're not usually going to name molecules with more than one functional group like this. Because if this, realistically, if this is a molecule that matters to the world at large, it already has a common name. And so more likely we just look up the common name and call it that. So I will typically be using this nomenclature, but I'm not going to mark you wrong if you use it that way. You can also have, I don't know what happened to my molecule there, a diene. What do you suppose a diene is?
More than one pi bond.
More than one pi bond. So if I, just knowing that, if I said, what's the structure of 1,3-butadiene, what would that structure look like? Take a guess.
Can you say it again?
Sorry, 1,3-butadiene. 4 carbons.
With a double bond starting at 1 and 3.
Bingo. Right, so if our suffix is something that indicates a functional group, sometimes we'll just throw a prefix in the middle of our suffix. We just like modifiers all over the place when it comes to this nomenclature, but if you get the hang of how it's used, it's actually pretty predictable. So for instance, if I said 1,2-ethane-diol, we haven't learned naming alcohols yet, but I just told you, as an example, that OL means alcohol, right? So what do you suppose a diol is? 2 alcohols. In fact, 1,3-ethane-diol means we've got ethane, OH, OH. That one's better known as ethylene glycol, which is antifreeze. All right, so I'm not testing you on diol nomenclature at this point, but just as a reminder that, you know, at this point you guys have seen enough nomenclature rules that once you add a couple of suffixes or some of the vocab, if you will, you know, follow your gut with some of these, right? You guys do understand this, even if it's something you haven't specifically seen before. You could probably work it out. We also have to worry about cis and trans when it comes to alkenes. Because when we have a pi bond, as soon as we add a pi bond, we don't have freely rotating molecules anymore, right? So if we had a molecule that was, if we had 2-butene, these are both going to be trigonal planar, and the pi bond is going to be above and below right? The sigma bond is right in between the two. It's rotationally symmetric, so it can twist around however it wants. The second you add a pi bond, though, the pi bond specifically requires the p orbitals to be facing the same direction, right? That's what makes it trigonal planar. If you try to take this and twist it, what happens to the p bond, those p orbitals? They're now no longer able to overlap, right? So by twisting this molecule, we would actually break the pi bond. So just like with cyclo groups, we had to have cis and trans because we couldn't twist around without breaking the ring structure. We can't twist alkenes around either without breaking the pi bond. So we still have cis-trans isomers, although they don't really use that nomenclature for alkenes anymore. We basically use a priority system that's a lot like RNS. That's all based on the atomic number. So in general, but you still see this used, and we can still use it to describe. Cis means that you're forming, that you have your two groups on the same side of the pi bond. So either both above or both below. So the one that I have drawn here, I have both methyls coming out of the board towards us. Both methyls being in front of the board on the same side of the pi bond tells us that would be the cis or trans?
Cis.
Cis. Right, so trans would be across the pi bond. The other way that we name these, and this is sort of the more common way now, the problem with cis and trans is that cis and trans is going to be referring to the rest of the main carbon group. But if you have other things attached, your priority, if we're using RNS priorities and by atomic number, name these, you can have your highest priority substituents on opposite sides, but your main carbon group on the same side. So cis and trans kind of get mixed up sometimes with these. So to remove some of that confusion, we basically, the IUPAC way of naming these now says we're going to use the exact same atomic number method for assigning priority, just like we would for RNS. And then if they're on the same side, like this one, then we would name it as Z. Z, this comes from German, so we use, for RNS, we used Latin. For E and Z, it's German, and Z stands for Zusammen, I think. I don't speak German. I've had somebody confirm this. I think it's something like that. It's got same right in the name there. Or the other way to remember this, and I don't remember where I first heard this, I think it was in a textbook though, is if you say it with a really cheesy accent, a cheesy French accent, Z is this same side. Right, so now you can remember me making a fool out of myself to remember Z is the same side. And E is the opposite. E is German for entgegen, which means against. So E is something like that. Again, my German is very rusty. Entgegen means against, so if they're on opposite sides, it's E. If they're on the same side, it's Z. All right, so this molecule would be Z, or you could call it cis. The Z is better, fewer letters, more universal, because assigning priority just comes down to atomic number. We assign priority basically for each side of the pi bond. So, okay, well, here's my higher priority, here's my lower priority. Here's my higher priority, here's my lower priority. Brad?
Is it possible that your higher priorities aren't necessarily the same thing?
Yes.
As in that, not like that example?
So, yeah, so let's see. So for this molecule, on this side, on the left hand of the two pi carbons, we have a hydrogen and a methyl, right? So the methyl is higher priority. And on the other side, we have 3 carbons. So the longest continuous carbon chain goes that direction. But higher priority, we get carbon and carbon, and then carbon and chlorine. Chlorine is the tiebreaker, it's higher atomic number. So this would be the higher priority, even though this is the longest continuous carbon chain. So that's why we get away from using cis and trans, because looking at this, technically this would be a trans isomer, because the longest continuous carbon chain is across the pi bond. But it's Z because the highest priority carbon chain is on the same side. So E and Z is the less confusing of the two, because we want to name it by the longest continuous carbon chain that has all the pieces we care about. Right, so cis and trans is what you learn first, and it still gets used for rings especially, but it's sort of fallen out of favor for alkenes in favor of using this system instead. And so here's some more where you could practice assigning priority, deciding E and Z. We're going to skip forward to look at the mechanisms for 6 minutes. All right, so we already drawn this out a little bit, but this is the way it's drawn in the textbook. If it's a concerted mechanism, it's going to be 3 arrows at the same time, because your base has to be, we usually would write it as base, not a nucleophile. If it was more specific, we could be more specific. But if we're showing it acting as a base, as a Bronsted-Lowry base, we would write it just base with a lone pair, is stealing a proton. Those electrons are moving over towards the adjacent carbon, the carbon that has the leaving group, and the leaving group is leaving. Right, so the base is always attacking an adjacent carbon's hydrogen, not the carbon that has the leaving group, which takes a little bit of practice. Since the leaving group is really driving this, the leaving group leaving, it has to happen to make room for everything else. A lot of times it's still going to be the best option to make your first arrow leaving group leaving. And then that'll sort of remind you, okay, well then the electrons have to come from next door. If it's stepwise, leaving group leaves, and then we have the same other 2 arrows. Base steals a proton, electrons move over to the carbocation. Right? The fact that this is the same step for SN1 and E1 means you're going to get the same intermediate for SN1 and E1. It's just what happens after that that's different. It's elimination versus substitution.
So for the stepwise mechanism, has the interactions already started when the leaving group leaves, or not quite yet?
Not necessarily. Usually what this means is that if you have a low enough concentration of your base, then the probability of the base running into this molecule is pretty low, right? Low concentrations favor it happening in individual steps, because the odds of them bumping into each other are significantly lower. Right? So if your probability of a concerted mechanism drops because both of these concentrations are lower, this mechanism becomes more favored because the first step can happen on its own. And what I hear you kind of saying is there sort of an in-between mechanism where it's stepwise-ish?
Yeah, because if I'm just thinking about the first molecule and the leaving groups, it just seems like, oh, I'm going to leave because why not? It's kind of hard for me to swallow.
So remember, these are all probability-based things, right? Might be uphill in energy for your leaving group to leave. Like if that's our intermediate, where it's, a carbocation and bromide floating around, it might be uphill in energy, but these things are all bouncing around constantly, right? So at a given temperature, there is a specific likelihood of this happening. Some, 0.01% of the molecules are in this state at any given point, even without a nucleophile around or a base around. And so, your cat might only spend 1 minute out of every month on the highest bookshelf in your office, but that means that if you open the door at any given time, there's a probability that you find the cat on the highest bookshelf. A quick terminology thing, alpha carbons and beta carbons. Alpha and beta, we basically use Greek letters to indicate how far away things are. So the carbon that has the leaving group, we call it alpha carbon, like active carbon. The beta carbon is the one that's next door. So if it's a secondary alpha carbon, then there's going to be 2 beta carbons, 1 in each direction. And then it goes on further, but usually we're most interested in what's closest to things. So there are some reactions where you have a gamma carbon, but they're pretty unusual. You can have a gamma carbon, it just doesn't usually wind up making any difference for most of these things because it's too far away. All right, last concept here. These elimination reactions are regioselective, meaning we predominantly will make one product over another if there's more than one possibility. Regioselective means that so if you have two identical beta carbons, like in this case, these 2 carbons are identical, you're only going to make one possible product. However, if your beta carbons are not identical, we don't have equal probability of both carbons losing a hydrogen. When we actually do this, we usually get a combination of products. It's not stereoselective or stereospecific like SN2, where you only get one. We'll get a variety, but they're not 50-50. In this case, 71% of our product makes the 2-methyl-2-butene, and 29% makes 2-methyl-1-butene. What might be playing a role? The carbocation that we would be forming, except the carbocation is going to put the charge in the same spot either way. E2 and E1 is similar as well. So I'm not sure why I specifically called out E2, other than like we could make the argument for carbocation stability. That's an easier argument to make. But even if it's E2, it still favors one over the other.
My guess was orbital position.
Orbital position?
Yeah.
You're close. It turns out that the same way that carbocations are more stable, the more carbons you have around it, alkenes are more stable the more substituted they are as well. So when in doubt, you want to make the more substituted alkene. And we'll talk a little bit about this. This section actually has some interesting chemistry drama from the 1800s about the groups that were doing this research. So we'll talk about the Markovnikov rule and the Zaitsev product and the Hoffman product next week. But for now, we'll end with the Zaitsev rule. And it's Russian, so there's lots of different ways of spelling it in English. This is the most common way I've seen it lately. Sometimes you also see it Z-A-I-T-S-E-V. Same guy. Russian doesn't translate to English particularly well for names sometimes. The Zaitsev rule is you're preferentially going to form the more substituted alkene.
What does more substituted mean?
So our alkene in this case has 2 carbons attached to the alkene. This is the alkene group as a whole. So this has 2 carbons attached. That alkene has 3 carbons attached. So the most substituted you could be would be 4 carbons attached to the alkene. 3 carbons is more substituted than 2 carbons, which is more substituted than 1 carbon. Right? And so if you have a choice, make the more substituted one. All right, we'll end there. I'll double check the quiz questions this time so that I don't put you in over your heads again. 1 week in a row is enough for that. And watch the Canvas shell because in order to be going as slow as we are here, we've kind of fallen a little bit behind on some of the stuff that we would normally be doing as far as lab. Normally I would have had a lecture on lab stuff so far. So I'm going to see if I can find my recorded lectures from last year talking about things like IR spectroscopy. And if they're any good, then I might have you watch those and do an assignment over the break that kind of will get you caught up on as far as how to interpret your results from the steam distillation labs. Brad?
Yeah. Speaking of labs, for our write-ups, for our first one, I wrote mine making an assumption that my audience reading it is familiar with the material.
Correct. That's usually what you want to do. Assume that it's your peers.
Okay.
So maybe don't make the assumption that they know as much as I do,
Yes.
but assume that you can give it to anybody else in the class and they'd be able to follow what you were writing.
So that's okay. You don't
Yeah.
want us to write it as if it's someone.
No,
who's never-
you're not trying to present this material to a Gen Chem student.
Got it.
Okay? Good question.
Happy Thanksgiving, everyone.
Yeah. So with that note, so Sunday will still be the deadline for the quiz, just because I want it to be relatively fresh in your mind, and then there will be some sort of assignment. I'll try to not make it too over the top, but there'll be some sort of assignment for next week. It'll be remote that will get you sort of thinking about infrared spectroscopy and stuff like that. Okay.